Hi folks, my name is Jeff Kotz, and today I'm going to talk to you about describing data, displaying and exploring data. How exactly? Well, we'll get to things to know in just a second. First off, if you happen to recognize any of these PowerPoint slides, it may just very well be that you have this textbook here, Basic Statistics for Business and Economics by Lind, Marshall, and Wathan. If you don't happen to have this textbook or these slides, well, you got the video, so that should help you out. The things that we are going to talk about today are things like location, including percentiles, quartiles, deciles, tertiles, and how to use those things to draw a box plot. We're also going to talk about skewness of distributions so we can see its visual shape, but also the numeric calculations that go into translating those shapes into numbers. Take a brief look at the bivariate relationships we can display with a scatter plot. We're also going to investigate contingency tables, another way that we can demonstrate bivariate relations. We're going to start by talking about measures of position. Now, the standard deviation is the most widely used measure of dispersion. We talk about that a lot with the empirical rule, how we can get away with the mean and the standard deviation in many distributions that are normal, because many distributions are normal, that's why we call it normal, and how we can use that to help us understand 68, 95, and 99.7% of the data in a normal distribution. There are some alternative ways of describing data that include determining locations of particular values, one of which you're already familiar with. You're already familiar with the median. The median is the number, if you organize them sequentially, that's in the middle. In other words, that describes where half of all values are below then and half of all values are above. It's the middle. That's its position. But we can find the location of some other positions using this formula. So we can find the location of a percentile p by taking the total number of things that we have in our sample, that's our sample size n, adding 1 to it, then multiplying by this fraction over here, p over 100, where p indicates your percentile. So if you're looking for the location of the 50th percentile, which by the way is the median, it's the middle, you would put p in for 50. We can also talk about not just percentiles, which is out of 100, but we can talk about quartiles, which divide your data into 4 equal quarters. We can talk about deciles, which divide your data into 10 equal deciles, 10 equally sized things. Or percentiles, which if it's a percent per 1% is per 100, we can divide into 100 equal sizes. The percentile computation, again, is pretty straightforward. It's formalized like this. To formalize the procedure, we let L sub p refer to the location. If we wanted to find the 33rd percentile, we would use L33 for the 33rd percentile. In other words, what location does 33% of all of our data fall below? If we wanted the median, we'd look for the 50th percentile. 50% of all of our data falls below this value. There's the formula. So the number of observations is n, it's our sample size. And if we wanted to locate the median, we would take n plus 1 divided by 2. Well, p is 50. 50 over 100 is 1/2. Yeah, so it would be n plus 1 divided by 2. Or for any specific location, we can put in p. Here's an example. Here are 15, sample size of 15, 15 commissions at Solomon Smith Barney's Oakland, California office. Now, people are making somewhere around $1,400 up to around $2,400. Locate the median, the first quartile, and the third quartile for commissions earned. The first quartile would be L25, the median would be L50, and the third quartile would be L75. Our first step, if we were doing this manually, is to organize these data so that they are sequential. That's the lowest, that's the highest. We organize it horizontally here so that it increases that way. And second, we need to figure out what locations we need to look for. So for example, the first quartile is L25. It's the location at which 25% of all of our data is below. Our sample size is 15. We add 1. We put 25 in for p. Well, 15 plus 1 times a quarter is 4. So the fourth number is our 25th percentile. We come here. 1, 2, 3, 4. That number says 1/4 of our data is up to and including 1721. We could do the same thing for the 75th percentile. 15 is our sample size. Add 1 times this fraction over here says our 12th. Our 12th value is 2205. That's our 75th percentile. And in the previous example, we may wonder what happens if we don't get a whole number. For example, if there are only 6 observations, 43, 61, 75, 91, 101, and 104, they're already sequential. Well, that's a sample size of 6. If we wanted to find the lower or first quartile, we would use this formula here, 6 plus 1 times 1/4, or 25 over 100. There is no 1.75th thing in this series. So what we do is we locate the first value in the ordered array and then move 0.75 or 75% of the distance between the first and second value to get that first quartile. So for example, the first and second values here are 43 and 61. The reason we use the first and second values is because 1.75 is between 1 and 2. If this had been 2.75, we would have taken the second and third values. The first and second values because this is 1.75, and that's between 1 and 2. So we find the first value, which is 43, and the second value, which is 61. And then we find that whole difference there between 61 and 43, and we multiply 0.75 times that difference. That will take us the 75% of the way between 43 and 61. We add it on to 43, and we get 56.5. In other words, 3/4 or 75% of this difference is 13.5. We add 13.5 to here, and that's the 0.75. That's how we account for the 0.75 in the percentile. That sounds complicated, which was why we have technology. If you have a data set, I suggest, just like these 15 numbers here, we can give those 15 data points a name, perhaps data set 1. We can use this Excel formula, equals percentile, 2 arguments in the percentile function. First, what array or data set you're using. In this case, I call it data set 1 because I've named it using the name box. And 2, the second argument after the comma here, first argument after the comma, second argument altogether, is 0.50, 50%. What I'm looking for in this case is the median. So you can't put in p as a whole number to use this formula. You have to convert it to a percent. Well, you convert it to a percent by putting a decimal in front of it. This formula here, equals percentile, would give us the median. We can use our first quartile, our median, and our third quartile, along with our minimum maximum values to construct a box plot. It gives us 5 points along our data set that cuts us into the 4 equally sized pieces. For example, Alexander's Pizza offers free delivery of its pizza within 15 miles. Alex, the owner, aptly named, wants some information on the time it takes for delivery. How long does it take a typical delivery to make? Within what range of times will most deliveries be completed? For a sample of 20 deliveries, he determined the following information: the minimum, Q1, the median, Q3, and the maximum. Q1 and Q3 are shorthand for the first quartile and the third quartile, and we can see things here. Note that the question up here says, how long does a typical delivery take? Now, that indicates colloquially that we're looking for some form of central tendency. Before you were introduced to statistics class, you would most likely have said, well, let's take an average. Well, now that you're learning statistics, you know that most typical probably means mode. Most typical, most common, most often, yeah, that's mode. Well, for central tendency, sometimes that language gets thrown around in questions quite liberally. So we have to be careful to understand what the question is asking. In this case, we know we're trying to find a box plot. So when we say how long does a typical delivery take, maybe we're trying to characterize the wholeness, all of the central tendency, giving some other interval markers, perhaps the other quartiles, perhaps if we're using means and standard deviations, use an empirical rule or Chebyshev's theorem. We have to see what other context the question is asking for. We can see down here that we're looking for a box plot. Using a box plot, we know we have minimum, Q1, median, Q3, and maximum. And here's how you demonstrate a box plot. The first thing you do is you create the appropriate scale along the horizontal axis. This is univariate, so we only need one axis. The only variable we're taking account here is time. Step 2 is you put 5 points on here. You have to put the minimum, Q1, the median, Q3, and the maximum here. Well, that's step 2 and step 3 combined. You start with Q1, the median, Q3. But because you have these 5 points, you essentially have this box in the middle which describes 50% of your data. Because if this is 1/4 and this is 1/4, 1/4 plus a fourth is a half, 50%. So 50% of your data is always going to be between your two quartiles. 50% of your data is also going to be less than Q1 and above Q3. This is how I'm going to guess Alex is typifying. He's saying half of my deliveries take between 15 and 22 minutes. There's a tail over here, so it kind of leans one direction. It's not typically that we're going to see anything get delivered. We don't ever see anything delivered less than 13 minutes. So most things take about this long. Heck, 75% take between 13 and 22 minutes. And then another 8 minutes for this stuff over here. Now that tail on the right side is how we indicate skewness. In chapter 3, we talked about measures of central location, mean, median, and mode for a set of observations and measures. And we talked about central tendency and dispersion. But another characteristic of that shape, another characteristic of that distribution is its shape. There are 4 commonly observed shapes. There's symmetric distribution, which is the same on both sides, a positively skewed distribution, a negatively skewed distribution, or a bimodal distribution. These are common shapes. Now, the symmetric distribution looks pretty, as we would describe it, normal. It's bell-shaped. Now, there are other characteristics, particularly of a normal distribution, that separate it from this perfectly symmetrical. Heck, this bimodal one here is symmetrical too, but it's got its modes on both sides. And here it's symmetric about the mean, median, and mode. All three things are in the middle. This is pretty normal over here. We would call this one normal. Now, positively skewed and negatively skewed distributions we might see in something like salaries or income. We call it positively skewed because this tail leans towards the positive end of the scale. Negatively skewed because this tail leans towards the negative side of the scale. Test scores tend to be this way. Very few people trail off here, and there's a big lump here. Salaries tend to be most people make a little, few people make a lot. Now, bimodal distributions can have 2 modes where it's peaked over here and peaked over here. We can have a number of different things that have bimodal distributions. So these are the 4 typical shapes that we see in terms of skewness. Now, skewness describes shape, and we can have a couple of different formulas that calculate this. We have the classic Pearson's coefficient of skewness, which is just taking the mean minus the median, multiplying by 3, and dividing by the sample standard deviation. Or we have this one down here, which your textbook calls the software coefficient of skewness. Now, my function for the software coefficient of skewness is going to Excel, saying equals skew, and then putting an array within that function. That's my software version. I still find some practical utility in Pearson's coefficient of skewness, and I'll demonstrate that in just a minute. Understanding skewness involves looking at these 3 things, though. First of all, a coefficient of skewness, whether it's Pearson or software, will range from -3 up to +3. A value near -3 indicates considerable negative skewness. +3 would be considerable positive skewness. Go back here. This is positively skewed. So if you have a huge, on the left-hand side of your distribution, it goes up real big and then it tails off towards the positive side. that would be huge, close to 3 in terms of positive skew. If you have something that peaks over here and trails off that way towards your negative side, so the webcam, I'm not sure if that's going the right way. How about this one? That trails off towards the negative side, a big peak over here that trails off negatively would be close to -3. So -3 is considerable negative skewness, +3 is considerable positive skewness. Note that doesn't mean that a low value like -3 indicates little skewness. No, it indicates a lot of skewness in the negative direction. A value near 0 will indicate no skewness. A value such as 1.63 indicates moderate positive skew. Let's go back to this one though, a value of 0, which will occur when the mean and median are equal. If the mean and median are equal, like this, half of it's over there, half of it's over there, that means the median, as well as it's indicated x bar here is the mean. When the mean and median are equal, we have no skew. It means our distribution is perfectly symmetrical and there's no skewness. Looking at this formula right there, if x bar is 5 and the median is 5, no matter what our value is for s, 5 minus 5 is 0, which means our skew is going to be 0. Tougher to see using this software 1. Practical utility Pearson 1, software 0. All right, so now we've got some more data. And the following are the earnings per share of a sample of 15 software companies. So we have a sample here. And they're arranged from least to greatest. While we compute the mean, median, the standard deviation, we can use those three things, the mean, the median, and the standard deviation, to compute Pearson's coefficient of skewness. We can also, if we wanted to, use the software method to calculate this as well. Well, this is what we get. If we use the software method, by the way, 0.973 here is the number using Excel's skew function. So where I took these 15 values and said, give me the skew of those, Excel, boom, software like that, answer provided. This is the histogram that goes along with these values as well. So we can see in terms of the shape, there's a big peak over here and then a tail off to the positive side. The skew is about positive 0.97, almost positive 1, indicates a positive skew. I said there was some practical utility in using Pearson's formula, and here it is. If I were just to give you the sample mean is 4.95, which you can see here, and the sample standard deviation is 5.22, which you can see here, and we know that the median is this number 3.18, because half are below and half are above. I may not have all of this data. I may not have Excel, but I know that 4.95 is just about 5. I know that the median of 3.18 is just about 3.2. I know that that difference is about 1.8. Well, 18 times 3 is 54, so you add a decimal to that and you get 5.4. Divided by the standard deviation, which is 5.22, I know that 5.4 divided by 5.22, two things that are about equal when you divide them by one another, gets you a number about 1. I know that it's going to be a little bit more than 1 because that number is a little bit bigger than that one. But the practical utility is this. With a lot of rounding, a little bit of arithmetic, and this one formula, I can get within decimal dust, ish. I can get really close, within 0.05 of this, so about 5% of the software calculation for skewness, given basic summary sample statistics, this one formula. The practical utility is that you can get a pretty good estimate without a whole lot of effort, even if you don't have any software. More so, if the mean is greater than the median, there's always a positive skew. If the mean is greater than the median, you always have a positive skew. If your median would be greater, if this were greater than your mean, you'd have a negative skew. Now, the standard deviation provides an adjustment factor. So we don't really know. So this difference here of approximately 1.8, we don't know if that difference is big or if that difference is small. Our dispersion metric tells us about how far apart things are. So it's not until we divide by the standard deviation of 5.22 that we get a true idea or a truer idea of the magnitude of the skew. But if the mean, x bar, is greater than the median, it's a positive skew. And then the opposite is true. If the median is greater than the mean, it's negative. But if you can just remember this, and then the opposite's the other one. Mean greater than median, positive skew. Mean alphabetically comes before median. Remember them in that order. Mean greater than median, positive. That's skewness. So we covered some stuff there. Let's move forward on to looking at a couple ways we can examine bivariate relationships. Now we want to study the relationship between two variables. We call it a bivariate relationship. One variable, like a unicycle, is a univariate description, relationship, because you're not relating it to anything. It's just univariate. If you have two variables, like a bicycle, it's a bivariate relationship. One graphical technique we can use to show how two variables interact is in a scatter diagram or a scatter plot. In this, we need to have two variables. One goes along the horizontal axis, the other goes on the vertical axis, like these three here. In this case, we're looking at the age of buses and maintenance costs. For one bus, that's 1 year old, the annual maintenance cost is right around 4 grand, a little under. We've got 3 buses that are 2 years old and they have increasingly higher costs. For these 2 buses over here that are 5 years old, those are almost $10,000, between $8,000 and $10,000 to maintain those. We would call that a positive relationship between those two. In other words, as the number of years increases, the cost to maintain it increases as well. Let's go down to the second one down here. Auction price versus odometer. In other words, how many miles are on the odometer of the car and how much money you pay for that at an auction. Up here, we've got two vehicles that have about 10,000 miles on them. Their prices are around $5,600. There's one vehicle over here that's got 50,000 miles on it, and you can pay about $3,500 for that one. This relation here is one that we would call negative, because as the number of miles increases, the auction price decreases. So over here for buses and cost, for maintenance, more miles, more cost. Over here, more miles, less cost. Positive relation, negative relation. Now here, if we're trying to find a relation between height and salary, it doesn't look like we've got any relation, any relation between those two variables. So we might consider that to be no relation. If we look at the Applewood data we talked about before, we can see that there's 180 vehicles, and maybe we want to know if there's a relation between the profit earned on each car and the age of the car purchaser. Are you getting more money from younger people or for more money, or more money from older people? Well, we can make a scatter plot here. And boy, I can't see any patterns in that data. Across the x-axis here is the age, and across the y-axis here is how much profit you got from the vehicle. And that looks kind of like a shotgun blast. That's pretty spread out. I've got no idea if there's a relation. That's one drawback when you have, let's say, 180 pieces of data all plotted here. You might have a lot of overlap. You might not be able to see exactly what the pattern is. Also, if there's no pattern, you're not going to see one. So it's not just that there's a lot of data here, because you can have a lot of data indicating a clear pattern, or you can have a lot of data here indicating an unclear pattern. It's less to do with the amount of data, mostly to do with the relation, or the nature of the relation, how strong that relation is. But we'll get to talking about correlations much, much later. Another way that we can look at relations between two variables, bivariate relation, is using contingency tables. Now, a scatter diagram requires that both variables are at least at the interval scale here. Both of these are pretty continuous ratio level measures, and that's fine. And even back here, we were able to see something like age here. Well, this is discrete measurement. It's that is interval, or we call that ratio level here. We can't really get in between there. Regardless, those are metrics that we can use. We need at least interval scale in order to use a scatter plot. But if we have things that are nominal or ordinal, we might need to use another way to represent them that's not graphic, but actually includes counts and cells. And we'd call that a contingency table. A contingency table is a crosstab that simultaneously summarizes two variables of interest. For example, students at a university classified by gender and rank, two variables, gender, male and female, rank, freshman, sophomore, junior, senior. So we can take those, cross them with those, and we can create 8 cells. We can get a count of female freshmen, male freshmen, female sophomores, male sophomores, female juniors, male juniors, female seniors, male seniors. Those 8 is crossed 2 genders by 4 ranks. In the second example, we can see if a product is classified as acceptable or unacceptable that by the shift on which it's manufactured. So acceptable or unacceptable, acceptability is one variable. Day, afternoon, night. Shift is another variable. It has 3 levels. 2 by 3, we would have a crosstab of 6. Or a voter in a school bond referendum is classified to a party affiliation, one of 3 potential parties, and the number of children that person has. Again, number of cells can get crossed. From the Applewood data, we can look at whether or not these 4 different dealerships might be doing better at selling cars than other dealerships. What we've done here is taken a median split of the data. In other words, we're saying half of our sales were made for below the median and half of them were made for above the median. 90, 90. So it's a total of 180. And then for each of the 4 dealerships, we can see how many cars were sold for each of those dealers. Now, in these ends down here, just like the edge of your notebook, we call them the margins. This is the marginal total. These are also called the row totals, because if you add up 25, 20, 19, and 26, you get a total of 90 vehicles that were sold for above the median. Total of 90 vehicles were sold for below the median. In this margin, we can get some column totals. 52 vehicles were sold from the Kane dealership. 40 were sold from the Olean dealership. 45 from Sheffield and 43 for Tianesta. Now, which of these dealerships is doing better at selling cars for good profit? Let's take it apart. Right here, I'm going to start with Olean because it looks like half of their vehicles get sold for below the median and half for above. To me, that seems pretty central. If we're going to say that half are below and half are above, Olean kind of meets that standard. Similar with Kane. Now, they've sold more vehicles total, and they're one below, one above. So it looks like they're pretty even and their numbers above and below the median. But if we compare Sheffield and Tianesta here, we can see that Tianesta is doing something right. They both sell about the same number of vehicles, 45 for Sheffield and 43 for Tianesta. But while they sold 2 fewer vehicles as a whole, they sold 26 vehicles for above the median. Generally speaking, they're doing better than their fellow salespeople at getting the most money per car. Whereas Sheffield here may have a higher volume than Tianesta and Olean, but that's because they're selling cars for less, generally speaking, than what their fellow car dealers are selling for. They've sold more cars than Olean, but most of those below the median. In fact, Olean sold fewer cars total, but more cars for more profit. So maybe we can say they're more efficient or they can get more out of the resources than the other ones. When we come back to here to the scatter plot, we might even be able to put those ages into intervals. And within those intervals, we can create a crosstab like this in order to see where those chunks of numbers might occur. Now, again, it would be up to you to take that continuous data for profit. We can do a median split. We can do quartile splits. How to divide up the age. Do we get 4 quartiles of age? Do we say people in their 20s, 30s, 40s? Do we use any sort of other means to break that out? Do we create quartiles for this one, quartiles for this one, have 16 cells, and then count 180 different things within those cells? Perhaps. They're all different ways that we can chop up this data. We can create contingency tables with Excel using the pivot table function. Now, that's another story for another time. Super, super powerful. We're gonna get to that story. It's like the Hobbit for the Lord of the Rings type deal. It's real good stuff. But to conclude what we talked about today, we talked about locations, percentiles, quartiles, deciles, tertiles. Remember that stuff when we talked about LP? Yeah, back in the day. Mostly I'm encouraging us to use Excel. Name some data and use the percentile function. When you use the percentile function, remember to include the decimal point in the second argument, the one that describes the numerical percent. Second, we talked about skewness. It helps us understand shape. If the mean and the median are equal, then we have a symmetrical distribution, provided it's not a bimodal distribution. Bimodal distributions can also be symmetrical, but the one where the mean and the median are equal and looks like this, that symmetrical distribution is pretty normal. We can also have positively skewed or negatively skewed distributions. The tail, the direction the tail is going, will indicate whether it's a positive or negative distribution. If the tail is going towards the positive side, I think it's that way for you guys, going towards the positive side, then we would call that a positively skewed distribution. We can also calculate that numerically. Now, again, there's a computer something something formula in there, which I like to call equals skew in Excel. Or there's Pearson's formula, which when used shorthand as an estimate is a great way to get a number using just summary statistics. Talked about how scatter plots can be used to take interval or higher level data and convert it to a bivariate relation picture, or how if we only have ordinal level data, or if we want to take our interval or ratio level data and create some intervals for that, we can create a scatter plot to look at counts of information there. Pivot tables are going to be huge for that. Well, that's the stuff I wanted you to know. Stick around if you want to know more.